Welcome to the webinar recording of the Understanding Subsurface Fate and Transport presentation from the Back to Basics Part 1, Developing the Conceptual Site Model and Site Characterization Plan workshop that NMOA hosted in March 2018. The presenter of this presentation, Understanding Subsurface Fate and Transport, is Michael Smith from the Vermont Department of Environmental Conservation. Michael is an environmental analyst at Vermont DEC, where he has worked as a hydrogeologist for the state of Vermont since 1986, primarily in remediation of contaminated sites, but also in groundwater protection and low-level radioactive waste. He is also an active member of all the ITRC DNAPL teams and projects since 2001, and was a co-team lead of the ITRC DNAPL site characterization and fractured rock characterization and remediation teams. He is also a member of the ITRC Board of Advisors, or was a member of the ITRC Board of Advisors from 2005 through 2011. He has a Master of Science degree in Hydrogeology and a Master of Arts degree in Climatology and a Bachelor of Science degree in Geology. So with that, take it away, Michael.
Thanks, Jennifer. I appreciate the nice introduction. So with this Back to Basics course, for me as a geologist, the most important part often is understanding the subsurface fate and transport. One of the reasons is so you can do what you need to do. If you look at this picture on the left with drill rod with coal tar, that's an actual site where a lack of understanding led to some problems and a failed remediation. So the purpose of this really is to provide an introduction, the basics of what is necessary to understand contaminant, subsurface fate and transport, so you know where the contaminant is, where it's moving, what's happening to it, is it degrading, is it not degrading, is it a non-aqueous phase or is it dissolved phase? You really need to understand the contaminant fate and transport so that when you actually design a remedy, it might actually work. That's the hope. So our agenda is we're going to start looking at geology, hydrogeology, and then we'll talk about Darcy's law, heterogeneity, and some important concepts, and contaminant fate and transport. So once we get the geology and hydrogeology down, we'll start talking a little bit more about contaminant fate and transport, the actual fate and transport. So geology is basically the movement of this, under our geology module here. Basically what we're looking at is the movement of a substance, groundwater and contamination, through the subsurface. What we found that we really knew since 1920s with the oil business is that the movement through the subsurface is really in great part governed by the physical nature of the subsurface and how the substance interacts with the subsurface. So therefore, in order to understand the fate and transport, it's really important to understand the geology. An important goal of any site investigation really needs to be to at least identify the basic geology of a site, determine what effect it has on the contaminant fate and transport. Depending on the site and the contaminant and the amount released, you may need more geology, and other sites you may be able to do a little less. So examples of how geology can affect contaminant fate and transport really sort of starts out with simple things. In a coarse grain material, they think of a big sand or boulders, they more readily allow transport of contamination. And when you're getting finer grain materials, such as a silt or a clay, they're going to slow the contaminant transport and actually create contaminant reservoirs, which happens when the contaminants diffuse in molecular diffusion from the coarse grain materials into the fine grain materials. And these reservoirs can be really hard to remediate and are going to act as long-term sources of groundwater contamination in the higher flow zones. As the contamination migrates from the finer grain materials, it back diffuses into the coarse grain materials. And then also, you will find sometimes like very fine grain materials, such as the clay, are going to serve as a barrier to vector migration. There'll still be diffusion, but the water will have to flow around it. Now, here's a little bit more of an example. If you look at these slides, this is an actual core, and we don't always measure these things this closely. It does happen sometimes for research, but generally we're not going to be able to measure this. But this just shows you over a very short distance, you have orders of magnitude difference in the hydraulic conductivity. So if you look at this on a larger but you can see where it really makes a huge difference on the flow pattern or where the contaminants flow. So if you get nothing else from this short course, geology controls groundwater flow. This picture of the core again showing this slurry fine beds, which make a difference. And then you look at the other picture, you see how on a larger scale, the heterogeneities control the flow. And that is something also to remember. While of course geology, it does control groundwater flow, past and present land uses can also create significant flow paths and other issues. This is a coal tar site in Vermont. It's actually the same site where that picture in the very front came from. And then just a picture of a guy out pouring some coal tar on the ground. But we have here, we have a set of canals, which are preferential pathways, even though they're filled in now. And we have pipelines through the area which provide preferential pathways. So you really have to understand that past groundwater, past land use. So to start with this, I'll give you a 30,000-foot view of geology. We're not going to get a Bachelor of Science degree out of this course, but I'll try to just give you a little bit, just in general, what we're expecting in New England. Now, typically, the landscape in New England has been, to a really large extent, controlled by glaciers that covered us in the last ice age. Most of the mountains are fairly smooth by the glaciers, and although in New Hampshire we have some mountain glaciation, which really sculpted the glaciers, so their mountains are more craggy than we have, say, in Vermont or elsewhere. Now, the glaciers transport and deposit huge amount of unconsolidated materials. They pushed it in front of them. Also, water went to the glaciers, the bottoms of them, and this huge amount. So you can see if you go in Cape Cod, where the whole Cape Cod is an end marine from a glacier. Now, unconsolidated materials then, which were deposited, have then been reworked since the glaciers all melted by water, by rivers, and by humans, anthropogenic activities. So I'll go through a little typical what we expect in New England in the unconsolidated geology. Generally, most of the development's been in the valleys, and generally they started with water power in the 1800s or earlier. So that's where we're going to find a lot of our unconsolidated materials. Typical New England material is till, which is basically if the material is unsorted, it's what the glacier went on top of and just compressed very tightly. And we have cane terraces and moraines, which really on the sides of glaciers, and you often find these on the mountains still. And they may actually serve as aquifers. So I'm going to go down and look a little bit more. Let's look at the more detail. The till can be very thick. It's very heterogeneous because it's just not sorted. Just whatever is jumbled under the glacier. And then the grain size changes, material changes. It can be dry, but it's going to be fractured at a site where we have 200 feet of what we call basal till, which is very tight, very dry. But tetrachloroethylene perk made it through into the bedrock aquifer in large enough amounts that we were pumping pure perk out of the aquifer at one point. It's very compacted. It's very difficult to drill. You know your site is in till if you go out there and the drillers are complaining. It takes forever to drill. And it's also difficult to remediate, primarily because it's so heterogeneous. It's hard to get fluids in there, get fluids out of there. So till can be very difficult. Now your cane terraces, moraines, as I was saying earlier, it's deposited by the physical action of the glacier. Basically, it's often on the sides of the glaciers or on the sides of valleys. It's less heterogeneous than till. Often it's very sandy, and if you drive around through New England, you often see gravel pits on the sides of the hills, and that's generally going to be a cane terrace. And these may be unsaturated, but they're also an important place for recharge to bedrock aquifers, because when the rain falls, it will go in there and then flow on top of the bedrock. And if there's fractures or if it's a porous bedrock, it'll actually help recharge the aquifer. Eschers are great aquifers. They're generally deposited by streams that flowed underneath the glaciers and sorted the material below it. Generally, they're going to be sand or cobbles, but sand or gravel. Very high yield, very easy to map, easy to protect. Then we also get outwash plains. Not much in Vermont, but that's when the glacier melted. It just a lot of water went out and pushed all the material out for ways. An example of what you'll find in an outwash plain can be lots and lots of cobbles and boulders and very high hydraulic conductivity. And if you have to drill in there, it's very difficult because you can't do direct push. You have to sometimes use a sonic rig to try to really cut through the boulders. Now, end moraines is like Cape Cod end moraines, I understand. This material at the very end of the glacier, which is left there and has then been resorted. Now, you also have glacial lacustrine and marine deposits. So when the glaciers melted, and there's left a lot of material in front of them which act as dams, so you had glacial lakes. You had some really big ones. So if you look up down the Connecticut River Valley, most of Vermont, down to Massachusetts, there was Glacial Lake Hitchcock, which was very large and actually had almost like a sea, had very deltaic deposits, and you had clays at the bottom with low energy environments. And we also get marine deposits. A lot of places, because the glaciers had pushed the land down, basically lowered the elevation of the earth and allowed water to flow in. In Vermont, we had the Champlain Sea, where this ocean actually went up with now the freshwater seaway, but the ocean went up there and into Vermont in the Champlain Sea. And we have some really large marine clay deposits, and above that, deltaic deposits. We actually found whale fossils in Vermont too. So again, we're at this concept that unconsolidated materials in the valleys are going to be reworked by recent alluvial activity. So once they were laid down, things changed quite a bit as the ground was rebounding. At first, you had like glacial dams break and water flow out quickly. Then you had water flow changing as the land rebounded, and you get more water with the rain. It just basically creates streams which meander across the valleys, and they sometimes actually can be a help because they can rework the material so it's actually almost like a sand deposit. You know, I said also earlier, in New England, much of the early industrial development, many of our cities still are in valleys. And this is where the unconsolidated materials are often thicker than in the highlands. So when you have a contaminant release, it's a different type than when you're in the highlands, where it's more bedrock. So our bedrock geology in New England is really diverse. We have a mixture of igneous, metamorphic, and sedimentary. In the northern part of New England, Vermont, Maine, you get mostly igneous and metamorphic. As you get the southern part of New England, say Connecticut, you get some Triassic sedimentary rocks. So you have both types of rocks, and it gets complicated. A lot of structural. When the continents were moving back and forth, pushing, when North America would bang into the European continent, it would cause a lot of folding and floating. And then really strong structural considerations which control contaminants is important. And also you have to remember the different types of rock is a primary and secondary porosity. Primary porosity in sandstone is pretty easy to visualize. It's the pore spaces between the sand grains or in a sand deposit itself. Now, that's really, when you have sedimentary rocks, you will have some primary porosity. However, in the igneous and metamorphic rocks, you really don't have much of that at all. There's some micro, but not really. Most of our porosity is secondary, which is actually caused by fractures or brittle structures, bedding planes, faults. So in the sedimentary rock, you're going to find both primary porosity and secondary porosity. While in the igneous and metamorphic rocks, you're really limited to secondary porosity, which controls contaminant flow. So don't try to read this right now. You can look at your PDF of this later. This is going to give you an idea of what scale we look at, how that affects the fracture flow properties. We have macroscopic, mesoscopic, and microscopic. And so you can get an idea when you look at this. Let's say orientation, you can use mostly mesoscopic and macroscopic. Length of fractures is mesoscopic and microscopic, or macroscopic. But if you look at the aperture size, it's more microscopic and mesoscopic. So if you look at this, and give you a better idea of where to expect how you see which properties. So macroscopic flow is the big picture. It's regional or site-wide scale. And so you have regional factors influencing flow. The faults, the big faults, rivers, changes in lithology. And example of how faults do is we have a site in Bennington, Vermont with a lot of PFAS. And it's stuck pretty much in the carbonate rocks. The thrust faults on to the west and to the east have prevented it from going into the other type of rock, which has been good to keep the plume somewhat small. So when you start looking at this, you need to do remote sensing and terrain analysis to evaluate. You start looking at them from the big picture. What can we see? And when you look at this 30,000 foot picture, say remote sensing, terrain analysis, It's going to give you an idea of what to expect, where your orientation of fractures are, the length, what connectivity. Orientation is pretty common to have a north, northeast, south, southwest trend of fractures, primary fractures, based upon the folding of the mountains. Based upon you generally have a northeast, southwest trend in the Appalachian Mountains. You have some major structural considerations with that. Length of fractures is more of the type of rocks. Let's say you're in a schist, you may have a lot of small fractures, but in a very competent granite, you may have very long fractures. They may not be connected very well either. Now, start looking at karst or limestone, you have to look at that as a whole. I mean, you really can't, from this point of view, it's goes for with karst, you can really say for other rocks too. It's when you use a 30,000-foot view, consider it a whole and look for regional groundwater flow, anticipated regional groundwater flow. So overall, you can give this flow behavior as a continuous Darcy flow. When you get down lower, it's not Darcy flow in the fractures, etc. But at this point, you have to assume that. And then when you know where your structures are, which you can get from terrain analysis and from remote sensing and from published maps, it helps you direct your investigation at smaller scales. So again, you get this 30,000-foot view, and when you go into do the site itself, it helps you guide you. So a mesoscopic site is really where we learn the most. This is where you actually do the plume delineation, flow between boreholes. You do pump tests and boreholes and measure other wells, see what's happening. You can go into the hole itself with logging material and get the orientation of an aperture, the thickness or the width, the density, length, and connectivity of fractures, and influence of matrix characteristics. So you're in a sandstone where you do have primary porosity. So that's going to change compared to the matrix in a granite or a metamorphic, which is only flows in the fractures. So what you should do is, as I said, go into the boreholes themselves, do the logging, but also put your shoes on, boots on again, get your button, and go back out and you can map fractures in the field. It's important as a geologist to get out there and see what's really there. Again, will help guide you what to expect. And then you go into the wells. The monitoring wells in a fractured rock can be very expensive, so you get the most you can out of each one. You're not going to have as many as you might have in unconsolidated materials. So then you can start testing the wells. Now, what's the flow in the fracture sets? Is there turbulent flow versus Darcy flow? You can, especially in karst. Now, what sort of advection that follows the fracture or primary? You get entrainment in finer grained areas. You get dispersion because if the number of fractures connecting, the fractures are dispersed the contaminant flow based on where the fractures go. So this is your primary scale investigation, and we do your majority of our investigation and characterization techniques in this area. There's a lot written on this. It's worth looking up in the literature. The ITRC fractured rock document we published in 2017 goes much more detail about this. So microscopic, I have to be honest with you, I may not get down to the scale very often. But this is when you start really looking, fine-tuning your site and trying to understand what's going on. You might have individual fractures, matrix to matrix interaction. It's just the one fracture, what's it doing? Microscopic and individual fracture analysis. You get a core sample, you try to do the analysis in that one core and in the fracture you may have. Flow between fracture and matrix. That's important to understand, especially if you're primarily in sedimentary rock. But you also need to understand the morphology of the fracture. How rough is it? Was it planar? Is it not planar? And that will affect how the water flows through. Understanding by doing cores, is there a certain infilling in the apertures and the fracture spaces? And that can slow down water or change where the direction is flowing. And you also have diffusion and capillary flow, primarily in the sedimentary rocks. And plus, you also you look at the interface between fractures and matrix in sedimentary rocks, and what sort of storage effects you get. Just because you have a rock with fractures, it doesn't mean it's not flowing. I used to mine in New Mexico in sandstones, which had a ton of water in them, that didn't just fall in the fractures. They actually flowed in the matrix itself. So site-specific geology, when you first come to a site, this is when you really start this scale, mesoscopic scale. The first thing you do, your initial view of a site, is what published literature is there available. I mean, I have a site I know there's been a release. You immediately have to look for human health issues, but once you're actually trying to investigate the site, what published literature? There's often State Geological Survey will have something, or the USGS will have material. Universities can have quite a bit of material. Plus, there's also a lot of previous site investigation reports, because we're often in the valley. Over the many years, there's been a lot of releases. So many of the earlier investigation reports for your site and nearby sites. And then you look at the aerial photographs, and look for fracture sets, look for land use. If you can find changes, the photographs over years, you can see changes in land use, and what to expect. And then you also have maps, geologic maps, health maps. Again, they can help you figure out where settlement patterns were based upon the geology, and because it was easier to settle valleys and hillsides. So then, once you do that, you have to conduct a site visit. To really understand the scale of a site, it's really important to be at the site and walk around, see it. Too many people do site work just from a desk and never go out and look at the site. And that's really not the best way of doing it. So once you walk in the site visit, you can see for yourself, is the site in the valley, what sort of unconsolidated materials. It's going to give you a better idea if it's thick, or you see bedrock, you know it's shallow. When that specific geology, then you start, again, looking back at this present land and past land uses. I mean, you can see the present, give you an idea where water lines are. Also look at the historical information and figure out what the past land uses were. And then you start to develop your initial conceptual site model, and you conduct your site investigation to refine your CSM. We do talk more about the CSM later. Discuss this in the next module. So what I want to start now is talk about hydrogeology. And I think it's really important that we understand Darcy's law. I'll talk a lot about this because I think it's really neat and it works and it describes how groundwater flows. So basically, if you go back to this one, Henry Darcy is a Frenchman in the 1850s, an engineer, and he was doing sewer pipelines. And he figured out how to predict groundwater flow or water flow based upon the relationship of the water and the pressures. So the first thing you do is hydraulic head. The hydraulic head, if you look on this, it's H1 and H2. And in fact, there's two components. There's the elevation head, which is basically generally compared to sea level. And there's the pressure head. The pressure head is the fluid density over a specific weight of water. It's the pressure over the specific weight of water, which is fluid density and gravity. So there's also actually is a third, but we don't look at it in groundwater. It's velocity head, but that's not an issue in groundwater because it's not flowing fast enough. So basically, the whole thing is your head 1 is equal to head 2 with that change in head. If you go back to the first slide, DH, difference in head, is the difference in the head of the water table at the 1 minus 2. So we'll see that more later. So then if you do a monitoring well, which we all have done, you have to understand what that water table is when you're getting the data. And you have your point of measurement, which is your well screen. It can be small, it can be large. Generally look at the center of it, that's your elevation above sea level, and you have your pressure head above that. So inaccuracies that can be associated with incorrectly located monitoring wells. A lot of us have seen wells with very long screens. I would really counsel never to use those, especially don't cover cross. If you look at this picture, for different layers in the aquifer. If you look at the coarse sand, and there's clay, fine sand, and silty clay. What this screen is showing you, it's the water level in the well is actually the same as the water level in the fine sands. However, if you have correctly developed monitoring wells, if you look down the coarse sand, it's a confined aquifer, and your water table, your potentiometric head, is above the water table. This is potentially called an artesian aquifer, and so that's important. Then if you look at actually the well corrected in the fine sand, a small part of it, your head may be lower. But what this is going to give you an indication of, if there is flow through the clay or fractures, it's going to flow from the coarse sand to upwards to the fine sand, not the other way around. So if you have contamination in the fine sand, you may be in luck that there's less chance of getting down to the coarse sand. But if you leave that monitoring well open like that on the left, you're also creating a pathway. So if you have contamination only in the upper portion of the aquifer, you can actually allow it to flow into the lower portion earlier clean by incorrectly constructing the well. So what I said earlier, Darcy determined that there's a relationship between flow, which is Q, the area, and the head. Basically, the rate of water flow through a tube is proportional to the difference in the height of the water. That's the head between the two ends of the tube, and inversely proportional to the length of the tube. Now, we don't have a lot of tubes in groundwater, but this does fit pretty well. From this relationship, it's possible to derive a number of equations that help describe groundwater flow. First of all, if you look at velocity, which is that Q, the discharge, and that's basically liters or over area, volume over area. It also equals Q, small q, which is Darcy flux, which again is length over area over time, because you subtract it because that's what your answer is, because you have area in the bottom, and at the top you have flow, which is gallons or liters per minute. So when you put the two together, you end up with length over time. That's what velocity of Darcy flux is representing. And then from that, you can get hydraulic conductivity, which is H1 minus H2 over the length. That's your I, that's your gradient. And Q equals K, hydraulic conductivity, times gradient. So Q over A equals Ki, Q equals minus Ki. The negative is important because it's inversely proportional. So we'll get more into the hydraulic conductivity. Now, in regards to velocity, as I said, the Darcy equation really describes the flow in a tube. So we understand that flow in the subsurface really doesn't occur in a tube. It occurs in the porosity between the pore grains. There's a portion of that which is the effective porosity, or most of the flow. So basically, you take the V, Q over A on the bottom, because it's less, you multiply it times the effective porosity, which is a percentage. Now, the flow is also proportional to this coefficient K. In hydrogeology, this needs to be adjusted to account for the formation. So Q, like we talked before, equals KIA. Now, little k, which is intrinsic permeability, Darcy permeability, is a C with a dimensionless shape. So it's a constant based on the shape of the sand grains. We'll never really know that, but that's essentially what it is, times the square diameter of the matrix grains over top the viscosity of the fluid. Now, it's really important to remember that, because the viscosity of the fluid changes. So generally we're thinking of water, so it's just going to be 1 cent, wherever the figure is. But when you change it, you have some light, lower viscosity materials, such as a dry cleaning solvent. The materials that fluid's going to flow through more quickly than water. Conversely, if you have a higher viscosity material, such as coal tar, that material is going to flow much slower. And on that equation, that should be rho G instead of G. So specific weight of fluid times your Darcy permeability over viscosity of fluid. So you have some issues with the Darcy law. The Darcy law assumes that it's saturated flow only. It assumes it's steady state. It assumes it's flow in the aquifers and not really the lower K areas like clay. It assumes all the flow is homogeneous, all the flow is isotropic media, and it's all in granular media. However, that doesn't necessarily affect the real world, but we can still use Darcy's law. The actual real world is more of a mixture of saturated, unsaturated flow, steady state, and transient flow. In fact, you really say there's no real steady state, because it's always changing. More rain gets changed to the flow, contamination is degrading or getting more contaminants, it's moving. So you can at best come to sort of a dynamic equilibrium, and the flow is definitely transient. We do have flow in aquifers and aquitars. Sometimes that flow may be more electrolyte diffusion than actual flow, but you do get flow in the locating materials. They also have homogeneous and heterogeneous systems. In fact, most systems are not homogeneous. If you look at pictures we showed earlier, there's going to be heterogeneities. That affects the flow. The flowing more through the higher K, the bigger pore spaces zones, than the lower ones. There's also isotropic and anisotropic media. So isotropic means it's the same everywhere you go vertically, and heterogeneous material means homogeneous means the same everywhere you go horizontally. But that's not the way the real world works. So it's heterogeneous and anisotropic. And plus we have flow in both granular media and fractured rocks. This is a picture, again, to show you why geology is not all homogeneous. High energy deposition See in one picture on the left, you see wave marks, ripple marks from when the machine moves through. And on the right, you see where sands and the water is moving back and forth. So nothing is consistent. Excuse me. So now we're going to look at where the highest amount of groundwater flows. Now, we're looking at, well, we do have flow in the lower K zones. The highest amount of water is flowing through some of the soils which are much more conductive. And many soils are not very conductive, clay or silty clay, loam, silt. But if you have sandy loam, and actually get sand and boulders and cobbles and gravel, those are where most of your flow is. And the high energy environments typically are heterogenetic and anisotropic. Leading down, if you go back to your initial geology class, when your stream's moving across, you have certain areas will deposit the more coarse material, and other areas where it deposits the clays or silts. So what we do to look at this is we have to go back to averaging. So what we can do, it depends on the site and the scale you look at this, but we have what we call representative elementary volume. If you look at this picture on the left, you can see there's larger sand grains, smaller grains, and the water's going to be moving to that porosity. So what you can do is, depending on what you're doing, you can pick a representative elementary volume. The bottom one is nothing but the sand grain or aquifer matrix. We get a lot of flow in there, but the top right really gives you sort of an average of the flow, and that's where you need to understand what's going on. You can never understand the micro flow through these small pictures, but you can get an average of the flow. But it's interesting. Tice is the person who did the equations we all do we learned in graduate school for doing groundwater flow models, and they work. And these things really work well. They're based on Darcy, and they work well if you're modeling groundwater flow, say for water wells, because it averages over a whole area. But in 1967, he was a smart guy, and he said at a conference, in a paper he wrote, it's certain that we need a different conceptual model, looking at the known heterogeneities in aquifers to explain phenomena of transport and groundwater. We really weren't looking a lot at contamination in the 1960s. It really wasn't until the 1980s. But he was thinking ahead and really realized we need to understand the geology if we want to understand contaminant transport. So now we'll talk a little bit about the contaminant fate and transport, dissolved phase fate and transport. So here's just a couple pictures to give you an idea. So most aquifers, the injection, the physical movement of the contamination in the water is the dominant mechanism for dissolved contaminants. And it's the simplest equation really is to describe how fast contamination is really look at the average velocity of the groundwater. If you average linear velocity is feet per day, after 10 feet per day, your contaminant might move 10 feet per day. But you need to throw in there the effective porosity. It's important to maintain that and understand your conductivity. And it's also driven by the head. So the higher the head, the more velocity you're going to have. But interesting, the picture on the right there is actually a real-world picture. And it's looking at the variations in contaminant transport over one transect. And it shows you what we've been talking about before, that certain areas carry most of the water. It's 90% of your flow is generally could be 10% of your aquifer. And this is showing you the same sort of thing. But your actual contaminant mass is only in a small portion of the aquifer. Now, what we used to look at in unconsolidated materials is hydrodynamic dispersion, dispersivity. Yeah, and that basically, if you look at that picture I tried to show, basically as the contamination moves through a porous media, the water has to flow around pebbles. This is going to spread out the water. It's sort of the classic view in this picture on the right-hand side is you have a source, and by the time you move X feet down, it's spread out from the dispersivity. But with our understanding, really sort of in the last 10, 15 years of really exploring heterogeneity in groundwater, dispersivity is less of a dominant spreading mechanism. It will obviously happen in the homogeneous areas or in the representative elementary volume of similar materials, but they won't get this view we have here on the right-hand side. Now here's an example of why heterogeneities. This is a Borden aquifer where they were pouring perk on the ground, and graduate students were getting out there digging up basically with a teaspoon. But it shows you that the distance of contaminants over these meters is extremely different. even you're in 4 meters area, you have change variances from 1 meter to 7 meters, just in a small area. So we can simplify subsurface and homogeneous isotropic. It's worked well for water supply, but has not worked well for remediation scale geometry. Remember, the anisotropy replaces isotropy, and it's a non-ideal behavior as is pronounced in the vertical. So let's go back a little bit to, again, this length of scale. With diffusion starts to replace dispersion as plume behavior. Now, so the heterogeneity and isotropy lead to numerous small-scale plumes. Here's on the left again is the sort of classic view we were all taught, where it's spread out evenly. But you actually look at a real world, there is some spreading, but it's confined to small areas. So these higher K areas could be a stream channel, it could be a variety of things. So let's go to molecular diffusion. I mean, I don't plan on discussing the equations, but if we'd like, we can start with a fixed law, a fixed second law. Basically, it's just chemistry. It goes from high concentration to low concentration. I'm really simplifying it, but that works for this. And to get this to work, I'm going to show you a model which sees it much better. This is from Tom Sale, professor at Colorado State University, one of his graduate students. Basically, he took a sand tank, pretty small, and had dark layers of bentonite clay, which we all know are completely impermeable. So in a minute, they're going to start putting in water with a fluorescein dye. These are days on the scale. So I was going through, taking a picture. Now look at the dark areas. Immediately you can see a sort of halo of this fluorescein dye working its way into the clay. It's molecular diffusion. It's because the concentration of the fluorescein dye in the bentonite is so much lower or non-existent. So it starts moving through. And he ran this for a number of days, and then he turns it off. But you can see what happens is you're still getting the fluorescein dye because now it's back diffusing out of the clay. And when you put a well in, say, an area, and you have enforcement standards of 5 milligrams per liter or even lower, looking at PFAS compounds, you can see why it doesn't take much to maintain a plume above enforcement standards or MCLs. If you look at this, probably won't do it the whole 123 days, but it's interesting if you look at that big blob, while it's diffusing out, it's also diffusing in. The very small second one from the bottom pretty much is all gone now. But you look at this on a much larger scale, a real world scale, and it's much more important. So what we're going to do next is I'm going to start looking a little bit more about how contaminant fate and transport is affected by diffusion. Now the early time is when you say you just had a release, you may have a pool of DNAPL, dense non-aqueous phase liquid like a coal tar, you may just have an ongoing release of dissolved phase or a leak. You may have a gas tank that leaked. But basically you have that sitting there. And that's dissolving into the water, and it creates the dissolved phase plume that we all worry about. Now, if you look at this at the early time, your plume is dissolved phase and the NAPL, non-aqueous phase liquid. But you can see into a finer grain material, moisture flows in the higher grain material where the little lines, but in the finer grain material, you see diffusion starts going on in early time. Now this goes over a large area. It can be hundreds of feet or even thousands of feet. Wherever that dissolved phase plume goes, you have diffusion. Then you go to late time. Some sites never get to that, but many do. The back diffusion is really what the source is gone. The old DNAPL, whatever was leaking, has been removed. Tank was removed, all the gasoline was removed, coal tar was removed. But you still have a plume that stays there. So even if you clean up your source of material, you may have a plume that's going to be there for years because it's back diffusion. A lot of our sites we find are old sites, especially when we first started looking at these. So these sites are very hard to clean up because of the back diffusion, and the plumes are going to be maintained for years. If you have a new release and you get it out of there before you have much of this occurring, you have much more luck. So one way of looking at understanding the contaminant is the mass flux. All this really is the flux of the contaminant being carried per unit area of the aquifer. The one-dimensional equation is J equals QX, specific discharge, C concentration. So basically it's your Darcy flux in X direction and times the concentration, or Ki over effective porosity times concentration. It's It's the units of it's the contaminant flux for unit area, so it's mass over area over time. So it might be 10 grams over a square foot over a day. So the average is over that area. Now, if you look at a site in general, you can do the contaminant fate and transport. And look at the mass flux. Going back to what we talked about the heterogeneity, it can be really variable. If you go in there with flux meters and you start pushing, taking actual measurements of the flux, you will see there's very different in different areas. So a lot of these maps we get from sites show iso concentration counters, which indicate it's all nice area, but actually in reality it's not. So if you understand your flux, understand your groundwater geology, you actually understand where the highest area of contamination are, we can do the most good remediation. Excuse me. Here's an example to explain, looks at mass flux can be, in an area where you have all three of these areas, the fine sand, the gravelly sand, they all have a concentration of whatever contaminant at 10,000 micrograms per liter. But in the K in the fine sand is 1 meter per day. And the gravelly sand is 33 meters per day, and the sandy and the higher sand is 5 meters per day. So actually, the actual mass flux, you get 1 gram per day in the gravelly sand over that meter squared. You get 0.03 grams per day per meter squared in the fine sand, and you get 0.15 grams per day over meter squared in the sand. So the mass flux is, again, highly dependent upon the geology. So going back to pushing again, I say this all the time, understand your geology. Now, mass discharge is just the integration of the contaminant mass fluxes across the selected transport. This can be transected. It's you don't have to worry about the scary integration sign. We can do it a variety of ways, but really looking at what's going on over the whole area. Look at this picture. I think we've seen it before. That's our mass flux document. If you want to find more about this, the accuracy mass flux document. Again, you're seeing certain areas where there are highest flux is occurring, other areas which are more storage, not really transport areas. But it's the area of the control plane, the units of L squared. So you look at the whole area, what's happening over the whole area. And you can use mass discharge. It actually has a use. It's not just to understand the flow, but you can actually understand it to help you. In this case, we're looking at there's a well. It's getting some of its water from where the contamination is going to be, but more of the water is coming from where the aquifer is clean. So you can actually figure out the concentration in the well based upon the variance of the flux. So you have a flux across that whole area. You understand what is coming to the well. The discharge from the contamination is 2 grams per day, but if you have 600 gallons per minute, you may not even be able to measure it in the well. So you can calculate that. Again, go to the mass flux document, which will help you get more detail about this. So one that I've talked about a number of times is non-aqueous phase contaminant transport. Now, this is really important, and also it maintains, a lot of these sites have very long-lived plumes because of the non-aqueous phase liquid. So you have two types, dense non-aqueous phase liquid and light non-aqueous phase liquid. Look at the picture on the right, there's LNAPL hexane. We're all familiar with LNAPL being gasoline or fuel oil. It floats on top of the water table. Then you have the DNAPL, dense non-aqueous phase liquid. That's the picture on the left, which is red. Actually, PERC is never red, but they always dye it red so you can see it's actually clear, but they always dye it red. So that's become the color of PERC, I guess. So in order to help us understand functions, where NAPL is, how it's going to flow through the ground, and where you're going to find it, how is this going to affect contaminant fate and transport. Tom Sale, again from Colorado State University, and Chuck Newell from GSI, came up with this what they call a 14-compartment model to sort of help you visualize the life cycle of the site and where the contamination is. Assuming it's an apple site. So you have transmissive areas, and the source zone, and the plume, and you have low permeability areas. So if you look at the one area, the transmissive zone, you will have NAPL there. You may create NAPL in the low permeability. And that dotted line going out is an irreversible flux. It's going to go into vapor or into the dissolve phase. It can't go back. But the heavy line is reversible flux, where it can go from dissolved to vapor, and from vapor back to dissolved. Then you get down towards the bottom, you have absorption, which we'll talk about more, and also matrix diffusion, which are reversible. Now, the reason it's a 14-compartment model instead of a 16-compartment model is when you get an actual aqueous phase liquid, we're assuming there's no NAPL. but this will give you an idea where the fluxes are there. So again, with the NAPL, it goes from NAPL to the dissolved phase, not back. But once you're in dissolved phase, you can go from the transmissive to the low permeability zones. It moves back and forth and maintains a plume. So we're looking at NAPL properties and what affects the fate transport. There's a couple things you need to understand. NAPL properties: density, solubility, viscosity, volatility, and composition. And then how NAPL interacts with the subsurface media. I'm not going to talk too much about these. We'll talk about a little bit. These are, again, our DNAPL document, characterization document, and really important to understand. Look at viscosity. If you think of a coal tar, very viscous. If you think of perk from a dry cleaner solvent, actually less viscous than water, so moves faster. If it's volatile, you have problems in the unsaturated zone. Is it heavier in water? Is it lighter than water? How soluble is it? TCE, trichloroethylene, is pretty high solubility, 1,100 milligrams per liter, whereas PERC only has about 120. So the TCE DNAPL is going to dissolve a lot more quickly than the PERC will. So you have to understand, then you start looking at the interfacial interactions. Now I'll talk a little bit about these. The one I really want to talk about is most important, I think, is saturation to really understand. And really what it is, saturation, it's the percentage of the pore space occupied by a fluid with NAPL, air, or water, all three. It ranges from 0 to 1 or 0 to 100%. Now residual saturation is the saturation remaining when NAPL is no longer moved. So you have to understand your saturation and residual saturation. So you look at the top picture on the right. When your saturation, the percentage of the pore space filled with the NAPL, is less than the residual saturation, the NAPL is not going to move. You have droplets in there, so you get ganglia, referred to as ganglia. You get little pools on top of clay layers. Where it's not moving, but as water moves by it, it can solve and it'll maintain a plume. But when saturation is exceeding the residual saturation, this is a picture on the bottom right, NAPL can be mobile. Now, basically, NAPL moves just like water. It's driven by the head. So as long as you have a head behind a higher head on one end of the NAPL than the other, it'll keep pushing it through the area. Plus, you have to displace the water, which we'll talk about more later. And sometimes you have NAPL which is potentially mobile but not moving. That's where if you have a DNAPL site and you don't want to drill through clay, especially if you pull a NAPL on top, because it's not going anywhere right now, but once you punch a hole through there, it actually cause it to mobilize and move down. And the same with a lot of LNAPLs. Certain times of the year, they may be immobile, but once the water table comes up, it may allow it to move. So relative permeability is important to remember. That's the KR, and it's a nonlinear function of saturation. But basically, go back to those other pictures. If you look at the top, for groundwater is 1, K for groundwater is 1, NAPL saturation is 0. Water moves through. Now, if you look at the middle, the KR is higher because your relative permeability drops because that droplet of NAPL there slows the water down, has to flow around it. So then you get somewhere between 1 and 100%. And then when you have the formation full of DNAPL, actually the relative permeability to water will be 0, but 1 per NAPL, approaching 1 per NAPL. Now in reality, you often have some water on the soil grain itself as the NAPL moves through it, can't move it. So it's never 100% either way. You also have air and train, depends on where you are. But it just gives you an idea of why sometimes, if you understand the groundwater flow, it's not going to tell you the same flow of the NAPL. And it's not going to tell you what the groundwater is doing when you have a NAPL release, because the flow to the groundwater is going to be less. Especially obviously like a coal tar site. A big blob and the water all has to flow around it. So a couple myths about LNAPL I want to talk about. First one is that we say LNAPL enters soil pores just as easily as groundwater. That's not true if you think of a number 6 or bunker oil, which is really thick, really viscous, and it won't enter soil pores very easily. Whereas groundwater, which is much less viscous, will enter easily. Now you can hydraulically recover all the LNAPL from the subsurface. That's going to be impossible generally, because if you look back when I talked about the ganglia residual phase, pumping won't move that, or the immobile area pumping won't move that. All the soil pores and the LNAPL plume are completely filled with NAPL. That's not true. As I talked, you have water in there, you got water and soil, especially as the LNAPL water table moves up and down. Floats on the water table are capillary fins like a pancake. I have a better picture we'll show you in a minute, but this picture on the right is not how oil or gasoline floats in the subsurface. And then you have this sort of rule of thumb that came out at one point in the 1980s or early 90s, that the LNAPL thickness in monitoring wells are exaggerated compared to information by factors of 2, 4, 10. This is completely wrong. You understand geology, you understand the NAPL, understand what's happening with the water table, where the NAPL is, but you can't use some rule of thumb like this. Or the other one is that the LNAPL thickness in the monitoring wells is always equal to the LNAPL thickness in the formation. Excuse me. It isn't. Again, it depends on geology and what's happening. Now, if you see LNAPL in a monitoring well, it means it's mobile and migrating. That's not true. It may be in the monitoring well, it doesn't mean the main body of NAPL is migrating. And now also LNAPL plumes spread to groundwater flow. Now, they spread based on the geology. So they look for the higher K zones, the higher permeable zones for the LNAPL. So what you can have is as the water table goes down, the petroleum will travel through a certain area, a certain layer in one direction, but as the water table comes up, it can go in a different direction. It's based upon the head of the LNAPL and the gel in the formation. And the LNAPL plumes continue to move long after release is stopped. That's not true either, because again, you have to have something there to drive that head. Same with Darcy's law. H1, H2, Q equals A, KIA, where I is the gradient. No gradient, no flow. So here's an example of what it really looks like. A very simple cartoon of it. On the left is the pancake model. This is assuming the LNAPL floats on the water table, uniform NAPL saturation. But on the right is actually what you really get. Probably can be even more complicated than this. The NAPL, the red material, below the water table, you can find it. Depends when the water table's moving up and down, it gets smeared, gets stuck. You have LNAPL and water and the coexistent pores. There's also air in that picture. So once we've talked about NAPL flows, we're really going to talk about, what happens to the organic carbon retardation that dissolves contaminants during transport. So we talk about NAPL, how that moves. It doesn't degrade very quickly, but once we have a dissolved phase flow, it's what often causes the risk. So focus after this talk is primarily organic contaminants. Now, other than the fact that we have molecular diffusion, you also have the fact that these contaminants will be retarded during transport with sorption. Every organic contaminants have an affinity for organic carbon, so they will actually it's a physical, but they'll stick to it based on the contaminant concentration. And then when the lower concentration water comes through, it'll back desorb. Absorption is basically how you figure out what's going on. You have it's the concentration of the mass, in the matrix, and then C is the concentration in the water. But so what is sorbed in the matrix is going to be your KD times the concentration of water. You see star is the amount sorbed to the aquifer matrix, and the C is the dissolved phase. But KD is two things. It's the organic carbon coefficient. This is really easy to take when you're out getting samples. It's also very cheap. So for different type of geology you encounter, if you can, you should take this, because it's going to be huge if you have organic contaminant. And then the KOC is a partitioning coefficient, where FOC is organic carbon content. KOC describes the contaminant affinity. So KD is KOC times FOC. And so you get KD times C. You get an idea of what is going to absorb to the matrix. So now you can actually do a retardation factor. It's basically you have to understand the geology against the bulk density. It's your KD over top of your porosity. Actually, it should be effective porosity. So the retardation gives you how much is going to be retarded. It's reversible again, as I said. The amount of carbon in the soil is based on the amount of organic stored to the carbon is based on the concentration of the contaminated water. It's affinity for carbon. So if you have less concentration in the water going by, it's going to desorb. This is one of the things that maintains the plume longevity, even when the source has been gone for many years, the original source. Now we're also looking at, that's mostly what we're talking about is volatile organics. Another thing which complicates it is when you have semi-volatile organics. Generally, semi-volatile organics have very high KDs, and they're going to absorb to the aquifer matrix. It can be very hard to get them off because there's such an affinity for the carbon. So they aren't going to dissolve. You won't see as much dissolve phase. However, it's going to serve to colloidal particles in the groundwater, and they'll move with those. So this is important to understand. So when you're sampling groundwater, you do not filter them if you understand what risk there is. Because if you filter the sample, you're going to preferentially remove some of the colloidal materials, clay and other materials. And then you won't really understand what your risk is or what's there or what's transported. In fact, this is why the EPA actually came up with originally the low flow sampling back in the late 1990s, because it was thinking more about metals. It's also the setting of all organics. You do low flow sampling, and that way you won't get the big pieces, but you will get the colloidal particles, and you understand what's flowing into the groundwater. You also get some source of colloidal particles of volatile organics too. Now, metals I'm not going to talk too much about. And generally, they are relatively immobile in groundwater. But with typical groundwater chemistry, there's some adsorption, precipitation, chemiabsorption, ion exchange. It's much less likely to come back into the water. But however, changes in pH or especially redox can mobilize metals. That's why under landfills, we have a lined landfill. The water going into it doesn't have a lot of metals in it, iron or manganese. But underneath the landfill, you now have an anaerobic zone. And that actually is going to cause the manganese and the iron or whatever metal to dissolve into the water, move in the water. And so you get high iron and manganese downgraded in landfills. One of the proposed radiation for a landfill site like this was to put in a permeable reactive barrier, basically pump oxygen through it. Basically put in an area the water has to flow through. Pumping air through is going to oxidize it and cause the metals to soar back to the aquifer matrix. It hasn't been tried yet. We don't know how long it will last. There's some issues with it, but we don't know if it'll work or not because it may not last long enough. But we can find metals dissolved in liquids discharge surface and transport with them. So sometimes you'll have a solvent which is dissolved in something on the surface, so it can actually dissolve the metals into it and it'll move with that. So inorganic contaminants, go back to this low flow sampling without filtering is a must. For metals especially, don't ever use filters. Don't allow anybody to use filters for sampling for metals because you won't understand what is actually transporting with it. And for inorganic nonmetals, these include things like chlorides and nitrates. Now, as a hydrogeologist looking at contaminant transport, we don't usually address these. Well, you might find nitrates in relation to use of ample explosives, but they're really these are both very conservative. We call them conservative because they don't absorb the aquifer matrix. They actually can be used as a tracer. You can put chloride in the groundwater. It's going to move through. It's going to let you know where it's going, how much it's dispersed, how much dispersivity is affecting it, because it really won't absorb to the aquifer. The issue is if someone's well, it becomes salty because of the chlorides, or if it goes in the surface water where it does have a health effect on the organisms. Nitrates, again, you probably don't want to use as a tracer because it has a health effect, but it can be an indication of ample in groundwater, ample being ammonium nitrate fuel oil explosive, which has some more nasties in it, but this is what moves first because, again, you'll see this first because it doesn't absorb, and later the other constituents will show up. Now, some sites it really may be necessary to assess whether you have bioremediation as a remedy. We're using this more and more, especially with volatile organics, things like trichloroethylene, tetrachloroethylene, and others, especially with petroleum. And actually occurring bugs in the subsurface will eat this volatile petroleum very easily. That's why we don't have huge gas station plumes often, because bugs eat as much as dissolving off the LNAPL. But understand bioremediation, you need to understand the pH, what's the total organic carbon, so what kind of food is there for the bacteria because they use the organic carbon, what are the redox conditions with the dissolved oxygen, does it need a reducing environment? Depends on the aquifer type of bug. Some bugs work in very low oxygen or anaerobic areas. Others work in aerobic portions of the aquifer. Is methane there? How's that going to affect the relationship with the bug? Mineral and what other content are there? How's that going to affect? You have sulfate. What are the bugs that are already there? Maybe you have the genes, the ones that actually help you. There's a certain species of dihalococoides which will eat degraded chlorinated solvents all the way through to ethane. But that one species isn't present everywhere, so you may have to inoculate it. Or it may be present in just low concentrations in your area, so you may have to put nutrients in to get the population growing. What's the iron? What's the magnetite? That can take your bacteria demand. Oxygen demand. How much is it needed? So understand fate transfer is the very end of this. Generally, we'd ask questions if we could, but I think that what we need to just sort of consider is when you're looking at a site, try to look at the site as a whole, understand the interaction of the contaminants with the aquifer, understand the aquifer, and think about what the first picture I showed with the coal tar dripping off the drill rod. What happened there is they didn't understand whether the coal tar was potentially mobile. They didn't really understand the fate transfer of the coal tar. So they put a remedy involved capping or the area. Once they capped that area, compressed this very soft soil and peat, all saturated with coal tar. We had coal tar squirting out on the ground surface. So it's not understanding potentially mobile coal tar, not understanding geology. Thank you.
Excellent, Michael. Thank you so much. That was a lot of great information, and I know I learned a lot. So thank you very much. We're going to end the recording now.